So I remember being written by Ben last year sometime asking if I wanted to speak at Andre's conference. And I think I responded in under a minute saying, yes, of course, of course, of course. I'm so pleased to be asked. And I am. Andre was really influential on me mathematically. I want to, even to very recently, and I wanted to show you some of the things, and I wanted to show him some of the things that I've been working on recently that come directly out of many things that he did, and it was actually a little personally embarrassing when in Sergei's talk when he got to Berenstein-Zelevinskii triangle, I thought, oh right, that of course is the way that Andre was most influential on me mathematically, and I had completely left him out of this lecture. But thankfully, Sergei talked about that, so I can tell you other stuff that Andre did that has really excited me. And something that Sergei didn't talk about was this work from Zelevinskii from '85. And I don't know what who decided to transliterate his name which way, what time, but anyway, this is what it's published under. He was interested in the equi-oriented AN quiver, which just means we have a sequence of vector spaces, and we know their dimensions, and we're thinking about all the linear maps from one of these to the next. So phi1, phi2, phi3, up to phi(n). And let me let Ham be just the set of these. So I've fixed the V's, and I'm just thinking about the product of all of these Ham spaces from Vi minus 1 to Vi. I goes from 1 up to n. And on this great big vector space, there's an action of a group I'll call GL, and which is just the product of the GLs. And the way it acts is if you have a basis transformation on V1, then it acts on the phi1 coming in and the phi2 coming out. Doesn't do anything to the other phis, of course, and doesn't do anything to the composite of phi1 and phi2. And it does change phi1 and phi2, but it doesn't change their ranks. And so the invariance of the GL action, so GL was the product I equals 0 up to n this time, of the GL VI, are just, you look at all the ranks of phi I composed up to phi j. Here I guess I is more than j. And those are all of the invariants by Gabriel's classification of representations of a quiver like this. So you can wonder what do the orbit closures look like as varieties, and what Andre defined was the following isomorphism. He takes phi1 up to phi(n) and corresponds it to a big block matrix. And so it's going to be a big block matrix. I warn you in advance that the sizes of the blocks are not square down the diagonal. They're square down the anti-diagonal. They go R1, R0, R1, up to Rn, R0, up to Rn. There's going to be identities of those sizes coming along the anti-diagonal. And so of size R0, R1, these are the dimensions of my vector spaces. Just above the diagonal, there's phi1, phi2, up to phi(n), and everywhere else there's 0. Okay? So the way you should think about where this matrix lives is it lives inside, let me think about first, take this space, mod B. So what are these guys? Here, B is the upper triangulars in GL of the sum of these dimensions. W naught is the anti-diagonal. So this is the, so GL of the sum of those dimensions, that's where this huge matrix lives, right, in the sum of my dimensions. W naught is the anti-identity in there that Sergey talked about, the ones down the anti-diagonal. This guy doesn't have ones down the anti-diagonal. It's got ones like this, right? These are identity matrices. So that's because I've multiplied W naught for my huge group by W naught for a certain parabolic. The parabolic whose levy is the product of these GLs. And this is a Bruhat cell. Actually, the way I like to call, I prefer to call this an opposite Bruhat cell. When I have a B orbit, for me, those are the opposite Bruhat cells, and the B minus orbits are going to be the Bruhat cells. And how do you think about this space? This space. There's a section of this living up in the group, which is just matrices, almost like I had there. They've got these anti-identity blocks. Up here, they've got anything. Down here, they've got 0. Okay? And the way you think of that is you think what these two B's are doing. This B is taking my original W naught P, this guy, and it's doing upward row operations. So it's putting all this stuff up here, and it's mixing up what's on the diagonal. This B, doing rightward column operations, is fixing those again and turning them back into identities. So this is a picture up inside the group of this Bruhat cell. Now, this is not the full Bruhat cell. He's not setting up an isomorphism between Hom and the full Bruhat cell, because we also have these zeros up here. He's setting up an isomorphism between that guy and a certain Schubert variety. So B minus is the lower triangular matrices inside this big group. And this guy is the one who's, if I just took B minus pi z b closure, that would be these matrices. So why do this? Why set up an isomorphism between a vector space and this intersection of a opposite Bruhat cell and this Schubert variety? Why is this worth doing? And the answer is that all of the rank conditions that you have on your quiver representation turn into Schubert conditions on your matrix. So a Schubert condition on your matrix is a rank condition on a northwest rectangle. So in particular, imposing that you want all this stuff to be 0 is saying you want to be in this Schubert variety, and that's northwest rank conditions. I want this to have rank 0, I want this to have rank 0, I want this to have rank 0. But the other rank conditions you might worry about are you'd like your individual phis to have small rank. So you might say, I want this thing to have some small rank, and that puts a condition on the rank of phi 2. Or this to put a condition on phi 1. But you might also want a rank condition on a composite phi 2 circle phi 1. And if you put a rank condition on here, that magically actually is a rank condition on phi 2 circle phi 1. So a little bit of linear algebra to work out. So all of the weird, difficult to quiver rank conditions to worry about turn into what are well understood Schubert variety conditions, these northwest rank conditions on the matrix. And one thing that gets you, as in this paper later by Lakshmi and Maudyar, is that the singularities of these orbit closures are only as bad as singularities of Schubert varieties, which is not so bad, normal, Cohen-Macaulay, rational singularities. And also, I and Ezra Miller and Mark Shimizono used it to think about the equivariant cohomology classes that these orbit closures define as classes on this space, equivariant with respect to this group. It came out of Andre's wonderful isomorphism. So one thing that's a little weird about this isomorphism I want to emphasize that wasn't in any of those aforementioned papers is that there's more rank conditions available from the Schubert side that you don't think of on the quiver side. I could cut this guy here and say not only do I want phi1 to have some small rank, but I'd like some northwest rectangle of phi1 to have some small rank. Or I might cut in like that or something. There's a whole lot more strata that naturally arise from this inside this vector space that the quiver people don't see. And I claim that this refined stratification is simpler. So let me talk about that a bit. So let me define, given a hypersurface, well, let me say it this way. I want to tell you what's nice about Schubert stratifications that make them better than this quiver stratification, this GL orbit stratification on Hom. So let me have some notation. XV0 is going to be BVB mod B, thought of inside G mod B. So this guy is some Kac-Moody group. You might have thought, so the Kac-Moody group you should be thinking about right now is this one. It's a nice finite dimensional Kac-Moody group, but they'll be infinite dimensional later. And this guy is Burrell. And I want this to be BWB mod B. And I want to think of this guy as stratified by its intersection with these. So let me let Y be the set of intersections where here W is less than V in the Bruhat order so that this intersection is non-empty.
Minus, yeah. Because this is a...
Minus. There's the minus. Thanks. And, and so this is isomorphic to just the interval from 1 up to V in Bruhat order.
What is B minus for Kac-Moody? You probably don't want. Do you want the minus?
I do. I want this guy to be finite codimensional.
So you can do it for Kac-Moody?
Yes.
Infinite dimensional?
Yes. So this thing is finite dimensional, and so these intersections are finite dimensional. I'm still stratifying a finite dimensional vector space just by its intersection with these finite codimensional varieties. Okay? Varieties. So no, mine will not be affine. Pretty soon. Sorry, the question for those who aren't in this room was, do I just want my Kac-Moody groups to be affine? No. I will have much scarier Kac-Moody groups. Oh, I suppose. Next time. And even so, I can't go below here and have it be visible. So, all right. So why are these nice? So these strata they're normal, Cohen-Macaulay, and have rational singularities. And there's more structure. There's a Frobenius splitting. There's a Poisson structure, and these are T invariant and Poisson, and they're the only t-invariant Poisson subvarieties with respect to this nice Poisson structure on that vector space. But even better than the strata themselves, you should think of them all together. Something I probably shouldn't talk about too much. It's but I will in a couple of sentences. So let me say that Y is the coarsest stratification by varieties, irreducible varieties, that includes, for which xv open intersect x1 open is the open stratum. So what that means is, and part of this is that Y is ranked. So it's a ranked poset. And also a nice thing about it is it's EL shellable. So a nice thing that a poset might be, a ranked poset might be. So what is this telling you? It's saying if you rip out the open stratum, then when you have a stratification, if you rip out the open stratum, you'll get various closed strata, and they might be of various different dimensions. But the fact that this thing is ranked says no, they will actually all be divisors. Once you have those divisors, you can think, what else do I know must be in my stratification? Well, I can intersect those divisors with one another, and I will get a bunch of components. And each of those components must be in my stratification, because it's a stratification by irreducible varieties. Take those, intersect them with each other, decompose, intersect, decompose, intersect, decompose. If you do this, you'll get a whole bunch of varieties that must be in your stratification. And the statement is that this stratification is just given by that. It's the coarsest possible stratification you could have given this divisor. So somehow the whole stratification here on this vector space is given by one polynomial, the polynomial vanishing on the complement of the open stratum. And so I think of that as a very simple kind of stratification. And it's much simpler than the original GL orbit stratification on the space Hom, which has neither of these properties. So refining the stratification has made it simpler.
Well, combinatorially, it's more complicated, I presume.
I would say no. I mean, in the same way that I think of, so for example, let's compare. So the question was, is the stratification more complicated combinatorially? So let's compare the stratification of the Bruhat decomposition of the Grassmannian to that of the flag manifold. And a nice property proved by Joseph in BGG is that in the Weil group, if a Weil group element covers only one or zero other elements, it has to be of length. Well, if it covers only one other element, it has to be one of the simple reflections. And this isn't true in the Bruhat decomposition of the Grassmannian. You could have somebody who covers only one other thing and it not be of length 1. So this is a sense in which the Bruhat order on Sn is simpler than that on that G mod P. And similarly, that's happening here. I don't know. You should ask Lauren, who knows what EL shellable is. But I wrote it. I know that it implies nice properties like if you take any interval in this poset and you take its order complex, that's homeomorphic to a ball, or just Cohen-Macaulay. Certainly Cohen-Macaulay. Okay.
It means that you can label, EL means edge label, shellable. So you can label each edge in the poset by a number, so that for any two elements of the poset, one bigger than another, there is a unique path with increasing labels. Okay? And here you can use as labels a normal ordering of positive roots. So like which inversion is created when you move up in the Bruhat order?
Well,
Roughly speaking. Anyway.
I have a solution. So, a nice property that a poset could have. So this suggests that if you have a stratified space, or this plus some other examples I'll get to very soon. There's one more nice property that all these have, which is that if you take the open stratum and you take its complement, that is anti-canonical. So it's not just a divisor; it's an anti-canonical divisor. And I guess on a vector space that doesn't mean very much because the canonical bundle is trivial. So let me say better that it's T anti-canonical. It's given by a section of the anti-canonical bundle that's T invariant, and that's a non-trivial statement. And what that gets you is, therefore, by adjunction, the boundary of any one of these strata is also anti-canonical. So, or T anti-canonical. So another place where you might run into this idea of, or why you might think that we're getting an anti-canonical section, and on this variety is actually from the Poisson structure. So the Poisson structure gives you a section of wedge 2 of the tangent bundle. You can take that and wedge it up to its top power just before it dies, and you'll get a section of wedge 2k of the tangent bundle. The torus action is getting you a bunch of vector fields, which will live in wedge 1 of the tangent bundle. Wedge with those two, and there's enough of these that all put together you end up with something of wedge top of the tangent bundle, an anti-canonical section. And that anti-canonical section is what's vanishing exactly on the complement of the open stratum. So these are related, and they're also related to the Frobenius splitting. When you have a nice enough anti-canonical section on a variety defining characteristic P, you can use it to define a sort of Pth root on functions. So of course, when you have a variety in characteristic P, you can talk about the Pth power map on functions, and you can hope, is there also some kind of Pth root that would serve as a one-sided inverse to the Pth power map. And defining such things is, under reasonable conditions I won't get into, they neither exist nor are unique some of the time. But when you can do it, they correspond to pretty closely to, but not quite, to sections of the anti-canonical. So this structure is what's eventually giving the Frobenius splitting. Why is it worth mentioning that? It gets you that any intersection of closed strata is reduced. So when you have a stratification by some closed subvarieties, that means the intersection of two closed strata should be a union of other closed strata set theoretically. The Frobenius splitting tells you that it gets you that union scheme theoretically. All right, so this I thought about for a while, and I thought was all so beautiful. This plus Andre's isomorphism suggested maybe there are other stratified spaces out there that one should be looking for Zelevinskii isomorphisms with, that's identifying them with Bruhat cells, or maybe Bruhat cells intersected with Schubert varieties, in order to study the stratification. So let me define a Bruhat atlas on a space. So M is going to be a manifold, and Y is going to be the stratification, the collection of closed strata. is a bunch of choices, a Kac-Moody group G, a poset map from this poset opposite to the Weil group of G, and it should be an isomorphism with a certain order ideal in WG. So this is going to be some finite set. This will be some infinite set, and so Y has a certain maximal element M, and so Y op has a certain minimal element, and that should be corresponded to the identity in WG, and we should just get some stuff nearby the identity. So we should be getting the union over the points V in Y min of 1 up to, or let me call them F in Y min, I'll call this guy V, 1 up to V of F. So combinatorially, we're saying that our poset should look like this reasonable part of a Bruhat order, and therefore one learns good things about it like EL shellable. And also I want a open set UF inside M, open chart for each F in Y min. And I want an isomorphism of that guy with the corresponding opposite Bruhat cell. And this should be a stratified isomorphism.
This Y min is finite?
Yes, so Y is finite. So this, okay. So the stupid case to begin with is if M is an opposite Bruhat cell, then UF, F is just the central point in it, the T fixed point, and there's one chart and we're done. A more exciting example, and this is mostly due to Michelle Snyder. Her thesis is on the archive from 2010, is M is the Grassmannian of K-planes in, I say Cn, I guess I should say affine space if I'm going to say Frobenius splitting, let's say Cn. And here G is affine, it's a GLN hat. And I haven't told you the stratification I want to use on M. So how do I stratify? So I'm going to need a way of, given a point inside the Grassmannian, to tell you some combinatorial data about it, and some finite amount of combinatorial data, and then the fibers of that assignment will be the strata. So it's like back in the case of Ham, where I would take this list of maps and I would look at all of the ranks of all of the composites, and I would get a finite number of natural numbers that way. So here, I'm going to think that I've got V, an element of the Grassmannian. Let's say that V is the row span of the following matrix, V1 up to Vn. Okay, so this is a K by N matrix of full rank, K, and these are the column vectors. Let's think of this instead of just a list of N column vectors of height.
What is Grassmannian?
Grassmannian, yes.
Where?
K-planes and Cn.
Okay, this K.
But this vector space Cn has distinguished basis, is that right?
Yes, this is my stratification. My stratification will not be GLN invariant. Yes, and I will use the basis. Yeah. So I've got, so my element is going to be the span of these, of this k by n matrix. And instead of thinking of this as a list of n vectors, I want to think of it as an infinite list of vectors, but they will be periodic. Okay, so I've got this infinite list of vectors, and the invariance that I want to attach to this, I'm going to make a function from z to z. And what the function does, f of I is defined as the minimum of j more than I, such that vector I is in the span of vector I plus 1 up to vector j. Okay? So I get myself a function from the integers to the integers that says how far forward in your periodic list must you look before your vector is in the span of the vectors in that interval from I plus 1 up to j. So a stupid case is you've got a column vector that's 0, and then you get I equals j. Or you could have a column vector that's independent of everybody else, but it won't be independent of itself, coming n steps later. So the f's that appear here always have f of I between I and I plus n. But they are also periodic, that f of I plus n is f of I plus n, because that's how the vectors are. And what's not as obvious is that this is bijective. So that's how I'm going to think of the Weil group of this guy G. It's the set of f from z to z, bijective, with this periodicity property. So this is one of the models for the Weil group for this. And to be very precise, GLN is not a simply connected group. And so loops in GLN is not a connected group. And so the Weil group of loops in GLN isn't a Coxeter group. And that's OK. So this is not a Coxeter group, what I have here. But that's only because loops in GLN isn't a connected group. Loops in SLN would have been slightly different. And then I would have had not all functions from z to z. The average of f of I minus I would have to be 0. But I don't need that. So what I have here is a rule that takes a point in the Grassmannian and assigns to you an element of the affine Weil group. And that's how I'm going to stratify the Grassmannian and have the strata be corresponded with part of the affine Weil group. I don't get the full affine Weil group. I only get the parts with these conditions. So I only get a finite set in it. So this stratification of the Grassmannian was, I believe, first put forth by Lustig, thinking about total positivity, and studied by lots of people, by Postnikov, by Reach, by Williams, by me and Thomas Lamb and David Spire, and lots more since. So the stratification is very nice. Another way to think about the stratification is you take the Bruhat decomposition of the Grassmannian and you hit it with the cyclic group. You get n Bruhat decompositions, and you take their common refinement. That's this. If you take the complement of the open stratum, that is the usual Schubert divisor hit with the cyclic group. Take the union of those n copies of the Schubert divisor. And that's an anti-canonical divisor on the Grassmannian, whose anti-canonical class is ON. So far I've told you the stratification on M, but I haven't told you what group I want to use. And I've told you this part and this part. Well, if I told you this part and this part by telling you that part, really. And I haven't told you what the actual isomorphisms are. And I'm not going to. You should look in Michel's thesis. It's a right. So, but what she does, she says, take this stratification. So the minimal elements of this stratification are just the T fixed points on the Grassmannian. There's n choose k of those. Okay? So for each one of those, there's a fairly obvious open set on the Grassmannian, which is just the usual big cell permuted to contain that T fixed point. You take that cell, and it has now a stratification inherited from M, and Michel Snyder identifies that vector space with this stratification from the Grassmannian with a certain cell inside the affine flag manifold. Yes?
These functions f, do they have some other spurious properties or any function?
This is it. This is it. They have to be bijective, have this periodicity, and now this.
And then there is a non-empty cell.
Correct. Then the set of M's that do that is non-empty. That's right. So positroids are realizable matroids. Is the
And this property that it's a coarse stratification is also satisfied here?
yes.
Uh-huh.
Yeah. So the and there's a Poisson structure such that these are the only so when you have a Poisson structure, the sort of minimal Poisson subvarieties you can think about are the symplectic leaves. If you have a torus action, the minimal things you would think about would be the torus orbits. If you put these together, then you could call them, the minimal things are the torus orbits of symplectic leaves. And so I call these the T leaves. And I'm going to blame Ravi Vakil for this terminology. Anyway, so the T leaves in this case are exactly the strata. And also they're exactly the compatibly split subvarieties. So this is one of those. But this fact that the stratification is generated by the divisor, you could blame on this isomorphism. I mean, we knew it already. But you could say because we have these isomorphisms and the stratification is generated by the divisor on these guys, therefore it's generated on those guys. Okay. So one more interpretation that I thought you might be asking about of what these Fs are. So if you only impose this condition on the Fs, then there's an interpretation of what they are, which is they are juggling patterns. They are juggling patterns of periodicity n with k balls. And what this is telling you is you throw a ball at time I, and it comes down and lands just before time f of I. And the fact that it's 1-to-1 says the balls don't collide. The fact that it's onto says when you're about to throw a ball, there's a ball in your hand available to throw. We've got this periodicity property, and there's other stuff that's nice here in terms of the juggling interpretation, like the poset of one stratum being in the closure of another corresponds to one juggling pattern being an excitation of another.
Condition just means that you have a ceiling, so you cannot throw your ball too high.
No, this condition is really very bad from the juggling point of view. So the first juggling pattern you might think of is f of I equals I plus 3, with n equals 1, and 3 is more than 1. So this is just very unreasonable from the juggler point of view. This is very important. It says you're not juggling antimatter. That balls should land after they are thrown. All right, so this was, 2010. This and the Zelevinskii isomorphism from before were a lot of why I started getting into thinking about this possibility that this is a reasonable definition. I should say this stuff is joint with Xuhua and Jiang-Hua Liu. And I usually say both in Hong Kong, but Xuhua is now going to the University of Maryland. So you might say, okay, we have an example, but how could we possibly come up with more examples? How would I know to look for the affine GLN in the case of the Grassmannian? So if you have such a setup, how can you figure out what the G is? So I've got this map, supposedly, from YOP to WG. And inside here, there's the divisors. And they are going to the length 1 elements inside the Weil group. So if I'm trying to figure out what my group is, I can start making its Coxeter diagram whose vertices are indexed by this. I can start with this. So make these the vertices, these divisors, of a Coxeter diagram. But now, how do you make the edges? How much should two vertices be connected? So, how to connect? If D1 and D2 are divisors, so more specifically they are in my in my stratification of M, then I can think about the stratification they generate. So I've got M and D1 and D2, and now I intersect those. And what might happen is that I intersect and I get something irreducible. And in that case, I say this is the A1 cross A1 Bruhat order, and I will not connect my two vertices. Or it might happen that I intersect the two of them, and the intersection is reducible. Maybe it has two components. So I put them in this poset, and then I intersect those again and see what happens. And maybe I'm lucky and that's irreducible. And in that case, I will say this is the A2 Bruhat order, and I will connect those two vertices in my diagram by an edge. And it might happen worse that I intersect these two guys and it has three components, and then this is hopeless. There's not a Bruhat order that looks like that. With when I have two generators A and B, I should only get AB and BA and not other possibilities. So if I get more than two, or maybe I get two at first, but after a while I get more than two, if the poset that I generate using just these two divisors doesn't fit inside a rank 2 Bruhat order, then I declare that this is hopeless, and I'm not going to get a Bruhat atlas on my space. And what has been amazing to me is how frequently this has worked. That I start with a stratified space, and I do this, and I don't end up with three components. It has more of this Coxeter flavor to it.
But it could be that for any pair, it works fine, but then when you start intersecting three or more.
That's true. It could, and I have examples where it doesn't work. Yeah.
I want to confuse you. Take this A2 example and restrict it to just things contained in that E2, then it will look like A1 cross A1, but not actually come from it, right?
Inside the D2, you're saying?
Yeah.
That's true. That's true. So what that sort of has to do with is the non-uniqueness of this G. That there definitely are, it's easy to write down sort of stupid examples where you can have different G's working for the same M. And I'm trying to lead to a recipe here to give the simplest G, not in the sense of simple group, but maybe the most commutative G, where I have the fewest bonds between my vertices.
But if you finish the definitions, what can happen if you have this E1 and 2, and they again have 2, and then the next one has 1? And what this will be?
So if it goes down not very far, then I might say, oh, it fits inside a G2 Dinkin diagram, G2 Bruhat order, and I would put a little. So it might come if I go like one or two steps further, then I'd say that fits into a B2. If it goes 2 steps further than that, it fits into a G2. If it goes further than that, I give up. It's hopeless.
But do you allow
No, because eventually I want to get a Kasmudi group. So I want crystallographic. Okay. So let's see some examples. Here's a fairly, so let's start with the Grassmannian case again. K-planes and Cn. So here the divisors are the ith rotation of the Schubert divisor. And in this case, di intersect dj is irreducible unless I is equal to j plus or minus 1 mod n. So I have, these are my n divisors that are going to be the n vertices of my Coxeter diagram. And I say that if I've got two vertices that are far apart, I shouldn't connect them. And di and di plus 1 give an A2 diagram, or Bruhat order. Unless we're in this stupid case where k is 1 or n minus 1, and this is projective space. And then again they intersect in something irreducible. So put these together in avoiding the projective space case, and we get that the Coxeter diagram is what we had here. So this is a way to retrodict the group that was used in this example. I mean, her thesis is before I had this idea of Bruhat atlases. I'm giving you this ahistorically to present it. This is coming from that. It didn't. It was this. This was motivated by that.
But the assurance is kind of based on hope, right?
Oh yes, 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 yes.
You just pray hard.
That's right. And I go looking at interesting stratified spaces and ask, do they do this? And frequently they do not. I wanted to give you a couple of examples where they do. It's a theory of examples. It's not a classification theorem. Let's take our manifold to be G mod B. And let's take the strata to be the intersections of Schubert varieties and opposite Schubert varieties. And for those to be non-empty, of course, I want W to be less than V inside the Bruhat order. And unfortunately, G is my group for my Kasmudi group. So I'm going to have to take this to be H mod B, BH. And these guys are in the Weil group of H. Okay? Because H will not be G. So these are the Richardson varieties. And the only ones of these that are divisors are when this is the whole space and this is a divisor, or this is the whole space and that's a divisor. So there's two kinds. There's the Schubert divisors and the opposite Schubert divisors. And when you intersect a Schubert divisor with an opposite Schubert divisor, you get this nice irreducible Richardson variety. Irreducible means you don't connect them, right? That's this situation, the A1 cross A1 situation where you don't connect. If two divisors intersect irreducibly, then the vertices are not connected in the Coxeter diagram. So we get that the Coxeter diagram is two copies of H's. Two copies of H's diagram. So the Schubert divisors intersect one another in various ways that match what they would do inside that cell, and so sometimes reducibly, sometimes irreducibly, and they give you H's diagram, and the opposite Schuberts likewise, but they don't end up relating to one another. so disconnected from each other. Now there's this unfortunate thing that I've been so far talking about a Coxeter diagram, not a Dynkin diagram. And that's because I don't know when I have let's say I have something like this and it goes further and gets me B2, I don't know which is the long and which is the short. Right? The POSET can't tell me which of the two generators is the long or the short. Maybe something else is out there that I should be looking at, but I haven't figured out what it is. So I have to guess. When I have this Coxeter diagram, what should I use? What orientation, what length should I assign things to make it be a Dynkin diagram? And here it's pretty obvious, which is we should guess that we could take G to be H cross H. And then what would the POSET map be? Now it's going to be that WV is supposed to map, so here W is less than V, is supposed to map to the pair W naught V. And this is in the Weyl group of G. So that's the POSET map, and it does identify this POSET of pairs with an order ideal inside here. So that's not very deep. What's a little more interesting is if you take, so this theorem that part of it, half of it is due to Kazhdan and Lustig, 79, I believe, and the stronger version with both of the stratifications is due to me and Alex's Wu and Yang, and that's on the archive, is that if you take a point on here and take, so I've got some point W on my flag manifold for H, and I take the cell, the attracting cell for W, so that's just W applied to the big cell, so B minus B mod B, that's isomorphic to, according to what this should tell you, X W cross X sub W. So on the vector space level, I'm saying I've got a big cell on the flag manifold, and it's isomorphic to the attracting cell this way, the stable manifold and the unstable manifold. Okay, so that's not very interesting on just a level of this vector space is the product of those two vector spaces, or even T equivariantly. That's not very surprising. The interesting statement is that this is a stratified isomorphism. That the stratification here is the product of two stratifications. And again, how is this stratified? It's stratified by its intersections with Schubert varieties and with opposite Schubert varieties. So what Kazhdan and Lustig did was they just thought about the stratification of this by Schubert varieties, not Schubert and opposite Schubert. So they don't write down the same isomorphism we do, because their isomorphism only preserves one of the stratifications. So that's the Bruhat atlas for G mod B.
Do you understand those intersections? I mean, I don't quite understand what those strata are in this.
So this guy is stratified. This opposite Bruhat cell is stratified by its intersection with Schubert varieties, and this Bruhat cell is stratified by its intersection with opposite Schubert varieties. And so I'm saying every stratum here is a product. All those is a product statements are compatible by one giant isomorphism of stratified spaces. So Joseph suggests that instead of H cross H Langland's dual would be the more interesting guess. So, all right, so this was the boring guess. I agree. And I don't know how to set up a Bruhat atlas with the Langland's dual brought into things. Okay, so this was not a Gmod B example, and we did not get a finite dimensional group. We got the loop group. This was a interesting case where we ended up with a finite dimensional group again, either H cross H or H cross H dual. So what about Gmod P in general? And so I've only got a couple of minutes, so I'll tell you quickly what the answer is. The diagram. So let me do an example. Let's take H mod P, right? So let's take H to be GL 15 or so. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Excellent. Okay. So I've got GL15. And when I have a P, that means I'm using certain of the simple roots of G. So let's take these guys to be the roots that are used in P. Okay? The Coxeter diagram for H mod P. Well, I didn't tell you the stratification. The stratification is going to be the projected Richardsons. Okay, so I take the Richardson varieties up in G mod B, and I look at their image, or in H mod B, and I look at their image in H mod P. And I get a bunch of subvarieties there, and this is a wonderful, I can't use that word. This is an excellent stratification, and many things were proven about it before the statement I want to make now. So I've got the stratification, and I can apply this recipe to it, and it works. You find out that you can identify this rather complicated poset with an order ideal for inside the Bruhat order for a certain Kac-Moody group. And the way you get the Coxeter diagram is you take two copies of H's diagram, this one and another copy. The other one will be this guy flipped upside down. And what that upside down is coming from, it's coming from the duality involution on P. So this P is like GL4 cross GL5 cross GL3 times some radical. And what duality does is it flips those AK Coxeter diagrams. So the other one is glued on here. This is the Kac-Moody group you need in order to use cells of it to model the stratification on here. So not affine. Okay? However, if this is co-minuscule, then you get the affine diagram. And I encourage you to check that out in the DN and EN cases. It's magic that this crazy construction produces the affine diagram if this is co-minuscule and not projective space. So I've got a couple of minutes to tell you about two more examples. One is the wonderful compactification of a group, which I'm not going to have time to define. But I will say that now, and I want Y to be the double Bruhat stratifications. And so it's the B cross B orbits intersect the B minus cross B minus orbits. So that's the strata. Inside H itself, this is the double Bruhat decomposition of the group. And now this is an extension of it to the rest of the wonderful compactification of the group. And I will just tell you what diagram you get. You get one copy for, let's say I'm in this example, a copy of H's diagram for the B cross B invariant divisors inside H. You get another copy for the B minus cross B minus invariant divisors inside H. And you get another copy for the complement of H, which is, so the complement of H is the rest of the H cross H invariant divisors. And what De Concini and Procesi prove about the wonderful compactification is that those divisors are all smooth, and any intersection of them is smooth and irreducible. So that third copy is completely disconnected. But these guys are connected to one another. So this is somehow, so I like to call these, I don't know, well, no, maybe I don't like to call it anything. So this crazy diagram has actually appeared in the geometric representation theory literature, this work of Lee, Y. Lee, that, huh? Right, that Ben pointed me to. And so you should think of it as a sort of fiber product of two copies of the Nakajima doubling of the original Nigan diagram. So here's a Nakajima double of H, and here's another one, and they're glued together along the extra vertices. And I have no idea why. I have not been able to connect this story with the quiver representations that Nakajima uses these diagrams for. Also, if you rip out all of these divisors, all of these divisors, then you end up with a cell, which is the attracting cell of the B cross B fixed point. So all the B cross B orbits can be seen in the neighborhood of the B cross B fixed point, which is to say, if you want to just understand the B cross B orbits on H bar, like Springer did, then you only see this diagram. And the fact that you can identify that poset of B cross B orbits on the wonderful compactification with a certain interval inside this Bruhat order was also known. It's by Chen and Dyer. So I want to say one more thing, even though I'm over time, because it's another connection to Andre's work. And it is, the AN minus 3 cluster variety is isomorphic to the cone over the Grassmannian. So this is not affine. It's the well, I guess it is affine. It's the affine cone over the 2 Grassmannian. And so this is a stratified space. And one way to think about why it's stratified is it's a cluster variety, and so it's got a Poisson structure and a torus action. And every cluster variety has finitely many T leaves, is this result of Zwicknagel. So we could ask, can we identify this with, can we cover this with opposite Bruhat cells? And the answer is no, because it's singular. But this thing lives inside wedge 2 of Cn, the Plicker embedding. So maybe we could identify that with some opposite Bruhat cell, and this guy with some intersection of that with a Schubert variety. And I want to tell you how to do that, which is we take dn, and we let v of k be w naught for dn of k times w naught for an of k. Sorry, an minus 1 of k. So this is the one you chop off to get an minus 1. And then this guy you take to be vn, and this guy you take to be vn minus 2, where you chop these two guys off at the end. So one can identify this as a stratified space with a Bruhat cell, opposite Bruhat cell intersected a Schubert variety. And just exactly as in the example I gave at the beginning of Hom being identified with something like this as a stratified space in the first work of Andre that was inspirational on me. Thank you. Can I do this? I mean, oh, can I do this for other Grassmannians? No, I really don't think so. I think this is something special to the 2 Grassmannian. I'm trying to do it for other finite type cluster varieties. So the thing, if you're trying to do this for the cones over other Grassmannians, then you start seeing, wedge k of Cn here. And wedge k of Cn doesn't, the weights on it don't seem to look like the weights on a Bruhat cell. I mean, somehow the weights on a Bruhat cell have to do with, an adjoint representation, and that has to do with like a difference of 2 things, and that's the 2 that comes into here, as far as I can tell. Yes.
There is a generalization of notion of quiver called the bow, and bow varieties in return every quiver variety is the limit, but you might find it useful and might contain some of the refinements.
Huh. Okay. I will look into them.
Well, this example was the trace of generalization. Just consider assume what k or a case consider its one classification and consideration of varieties, orders of varieties. So, this is super simple scheme, just then get something.
So Joseph asks about what if, are there generalizations of this picture beyond wonderful compactifications of groups to wonderful compactifications of other symmetric spaces? And one thing that goes bad with other symmetric spaces, so one thing that's nice about this guy is the T action on it, all of the fixed points are attractive, which is something that's also true for the torus action on a Bruhat cell. And when you do this if you think about the T action on other G mod K bars, there will be certain fixed points that are attractive and certain ones that aren't. And so my hope is that you could get charts on G mod K bar nearby the attractive points, but not over the entire thing. And I think the attractive points are all. I think all the fixed points are attractive exactly if the Satake diagram for G mod K has only white vertices, which is this case and a few others. But in other cases, I don't expect to actually cover G mod K bar.